Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have our first contributed talk. The title is Randomized Block Krylov Methods for Stronger and Faster Approximate SVD in the line of recent work on randomized linear algebra that's become very popular. And the speaker is Cameron Musko, and the authors are Cameron and I guess his brother, Christopher Musko.
All right, so I'm talking about randomized methods for approximate singular value decomposition. The singular value decomposition, all of you probably know, it's the decomposition of any matrix into the product of three matrices, U, which has orthonormal columns, the left singular vectors of the matrix, V transpose, which has orthonormal rows, the right singular vectors of the matrix, and then this non-negative diagonal matrix sigma, whose entries are the singular values of the matrix and are typically ordered in decreasing order from sigma 1 through sigma d. The singular value decomposition finds applications in all sorts of places. In data analysis, it's typically used for dimensionality reduction and specifically for low-rank approximation and principal component analysis. So these applications are based off well-known optimality properties of the singular vectors as sort of the directions of greatest variance within the data set. So specifically, the singular vectors are the eigenvectors of AA transpose and A transpose A respectively. And due to these optimality properties, you can read off an optimal low-rank approximation from the singular value decomposition. So if I just zero out all but the top k singular values and their corresponding singular vectors, I get this rank k matrix AK, which minimizes the error A minus B Frobenius norm for all rank k matrices B. And this actually minimizes the error when you measure it in terms of any unitarily invariant norm. So an important other one is the spectral norm error. Now, AK can also be written as the projection of A onto its top k principal components. So I can write that as UK transpose A. Now, the singular value decomposition is somewhat of a complex object. What does it actually mean to approximate it? So I'll just review some standard approximation metrics. The SVD gives optimal low-rank approximation, so we can ask an approximate SVD to give near optimal low-rank approximation. Specifically, I want to return a set of k singular vectors, which I'm denoting here as U tilde, UK tilde. And I want, when I project onto these singular vectors and look at my Frobenius norm error with respect to my original matrix, that this error is nearly as small as the optimal Frobenius norm error for a low-rank approximation. Now, this is very useful in some circumstances, but Frobenius norm error can be sort of a weak measure of error. This is because the Frobenius norm of a matrix is equal to the sum of its singular values squared, and the Frobenius norm of the difference between A and its optimal rank k approximation is equal to the sum of its squared singular values below the top k singular values. Now, typically data sets display strong singular value or spectral decay. So these small singular values are small, but if you're in very high dimensions, this total size of this tail can actually be very large. It can be very large in comparison to the top singular values of the matrix. So the right-hand side of this inequality can be sort of large, and this approximation guarantee can be weak. Unless you set your epsilon to be extremely small, for many data sets, you can basically return any U tilde k and get pretty good Frobenius norm approximation when you measure it in this sense. So people look to give stronger notions of approximation, and one way to do that is just to use the spectral norm rather than the Frobenius norm. So the Frobenius norm is the sum of singular values of a matrix. The spectral norm is just the top singular value. So in this case, the spectral norm of A minus its best rank k approximation is its k plus first singular value. Due to singular value decay, this is typically very small if you're choosing k to be large enough. And so in order to achieve this notion of approximation, U tilde k really is going to have to project off the directions of largest variance in the matrix. It's really going to have to align with your top principal components. So this tends to be a much stronger notion of approximation than Frobenius norm error. A final sort of strongest notion of approximation we can talk about is we want our approximate singular vector U tilde I to nearly have as large of a dot product over AA transpose as the true singular vector AAA transpose. Okay, so that's approximating the singular value decomposition. We can do this all with classic full SVD algorithms, like the QR algorithm. These types of algorithms run in ND squared time. They have super good dependence on error, so things like log 1 over epsilon error rate. But unfortunately, n times d squared can be prohibitively expensive for large matrices. So the question is, can we do something better? Especially if we're doing principal component analysis or low rank approximation, we're really just talking about computing the top k singular vectors of the matrix. So the question is, can we go faster if we just want to compute this partial SVD? The answer is yes. If we're going for the weak approximation goal of Frobenius norm error, we can use like classic strong rank equivalent QR algorithms and get within a polynomial factor of the error. We can also use Johnson-Lindenstrauss random projection style techniques, these sparse subspace embeddings, and get within 1 plus epsilon of the optimal Frobenius error with a very fast runtime, something proportional to basically the number of non-zeros in your matrix plus some lower order terms depending on k and your epsilon. But as I said, Frobenius norm error is weak in many circumstances, so we want to do something stronger. And if we want to get stronger error things like the spectral norm or PCA error, really the only game in town are iterative methods for the SVD, and specifically the power method and the Lanczos methods. The runtimes of these algorithms are something like NNZA, which is the number of non-zeros in your matrix is the time to multiply your matrix by a single vector, which is the basic primitive of these iterative algorithms. K, the number of singular values you're computing or the dimension you're reducing to. And then iterations typically depends on your error and on some other parameters. K is typically much smaller than D, i.e. the dimension you're reducing to is much smaller than your original dimension. So as long as you keep your iteration count reasonable, these algorithms are going to be much faster than doing a full SVD using a classic algorithm. And so they're widely implemented and used all over the place. I'll briefly mention there's been a lot of recent interest in stochastic methods for PCA and dimensionality reduction. I'm very interested in these methods, and I've been doing some work on them and happy to talk about it offline. But I'm not going to directly compare them to the iterative methods because I'm mostly talking about the general matrix regime where these don't necessarily give speedups over the classic iterative methods. Okay, so let me just quickly review the power method, which is the most basic iterative method. Most of you know the power method for computing the top eigenvector of a matrix. And the block power method, which is also known as simultaneous or subspace iteration, is the direct analogy of this for computing multiple top eigenvectors or multiple top singular vectors in our case. So you start with a block of k vectors, some initial iterate, and in each iteration you're going to multiply by your matrix, you're going to orthonormalize the result, and this is going to give you your next iterate. As you multiply by your matrix, the directions in your vectors that are pointing in the directions of the top eigenvectors or the top singular vectors of the matrix are going to be stretched in comparison to the rest of the vector, and eventually your iterates are going to converge to spanning the top subspace of your matrix. So this is the basic power method, the block power method. Okay, the runtime for this power method you can give by the cost of a single iteration, which is NNZA times k, so this is the cost to multiply by k vectors, and then the iteration count. It's going to converge geometrically, so you have this log d over epsilon term, which is basically coming from if you have a random initial start matrix, you have polynomial d initial error, and you get down to epsilon error. And then the convergence rate depends inversely on this gap parameter, which is basically saying how much larger is the kth singular value from the k plus first singular value. Now, traditionally, this gap is sort of assumed to be a constant, but in many data sets, it's actually going to be the dominant factor in the iteration count. So as I explained, most data sets display strong singular value decay, but after the initial decay, the spectrum really flattens out. This is a adjacency matrix of a social network graph, and after about the 30th singular value or so, the spectrum looks quite flat. If I look at the median gap amongst the top 200 singular values, it's only 2 out of 1,000. And if I look at the minimum gap, so if you choose the worst possible k, if you get unlucky, this minimum gap is something like 1 out of 25,000. So if we plug this into the runtime bound we gave before, we're getting this 25,000 multiplier on our runtime, which is really bad. And this doesn't really jive with what's seen in practice. The power method seems to work very well in practice, even if there are very small singular value gaps. So this phenomenon has been largely explained by recent work, which gives gap-independent bounds for the block power method with randomized start vectors. Specifically, in log d over epsilon iterations, you can get within 1 plus epsilon of the optimal spectral norm error for this singular value decomposition. So essentially what they're doing is you're replacing this gap parameter with your epsilon parameter, your error parameter. And this improves on the classical bounds whenever epsilon is set greater than this gap, which is often the case in practice. There's been a long line of work on this. Probably the most well-known paper is this Halko, Martinsson, Tropp overview. And subsequent to the release of these results, there's been a lot of renewed interest in this randomized block power method. It's a very simple algorithm. It gives simple runtime bounds. And so it's been implemented all over the place recently. This is sort of in contrast to the fact that in the numerical linear algebra community, Krylov and Lanczos methods have been used over power method. They've been long preferred over power method. In Lanczos methods are really the standard implementation of SVDs for large matrices. So MATLAB SVDS, this is using a Lanczos method, not the power method. So why is this? This is traditionally because the Krylov and Lanczos methods essentially allow you to put a square root on this gap parameter that I was talking about. So if you have a small singular value gap, these are going to give significant acceleration in comparison to the power method. The recent work on the randomized power method is removing the gap dependence on power method and putting an epsilon dependence there instead, so showing it works in the small gap regime. But up until now, there's been no gap-independent analysis of Krylov methods. So that's what we're providing. Our contribution is basically showing you can get the same acceleration when you have a gap-independent bound. You can get the same acceleration when you have a gap-independent bound, getting the square root of epsilon parameter. Okay, so our main result is there's a simple randomized block Krylov iteration that gives all 3 target error bounds in this runtime. The number of iterations is log d over square root of epsilon. This is giving a bound that's independent of our matrix A. So in classical analysis, if you happen to have a gap of size 0, you get literally no guarantees on your performance. Our bound will still be useful in that case. It beats the runtime of block power methods significantly for small epsilon. It again improves on Lanczos whenever your gap is smaller than your epsilon parameter. So the first step in understanding how we can remove the gap dependence is understanding where it comes from in the first place. It basically comes from the fact that classical analysis all depends on convergence to your true top singular vectors or your top subspace. And they measure error using a potential function, something like ui minus u tilde I, the 2 norm. This is a simple potential function. Once you can show that you make this potential function small, it's easy to show the type of error guarantees we care about. But there's a huge negative in that in order to get ui minus u tilde I small, you inherently require an iteration count that depends on your singular value gaps. So specifically, if I apply the power method when I have a small singular value gap, I'm going to converge quickly to the top singular vector, but I'm going to converge very slowly to the second singular vector because it's only boosted in size a little bit at each iteration. The thing that we can notice though, so this may seem like an issue. We have this inherent gap dependence if we want convergence. But the thing that we can notice is that convergence becomes less necessary precisely when it's difficult to achieve. Specifically, if I have a small singular value gap, it really doesn't matter if I can distinguish the second from the third singular vector. In terms of principal components or for low rank approximation, these 2 singular vectors are pretty much as good as each other. So while minimizing this ui minus u tilde I is a sufficient thing to do, it's far from necessary, especially when you have a small singular value gap. So this is why the intuition for why you should be able to remove this gap dependence. How we do it technically speaking is that instead of thinking about convergence between subspaces or singular vectors, we're viewing iterative methods as denoising procedures for random sketching methods. If I have an actual low rank matrix, a rank K matrix A, I choose a random Gaussian matrix with K columns and I look at the span of A times this Gaussian matrix. This is equal to the span of A with probability 1. If I project A onto this span, I'm going to exactly recover the matrix and I'm going to get optimal Frobenius norm reconstruction for this low rank matrix. Now, if my matrix A is not actually low rank, so it has some distance from low rank, A minus AK, I'm going to instead get an error that's polynomial in this optimal Frobenius norm approximation, polynomial in A minus AK. This is basically giving an error bound for a single iteration of the power method. It might seem very weak, and it is very weak, and unless A minus AK is very small, but it gives us a starting point. Because now what we can do is instead of applying this very simple sketching method to A, we can denoise A and apply instead to this matrix AQ, A powered up to the qth power. This is exactly what block power method does. You iteratively compute AQ times G, and then you return its span as the output of your algorithm. AQ looks exactly like A, except that all of its singular values are raised to the qth power. So if we look at the spectrum, what's going to happen is in AQ, the large singular values are going to be significantly blown up in comparison to the small singular values. If I scale the spectrum so they match on the top singular value, basically AQ's tail is extremely relatively small. If I look at its optimal Frobenius norm reconstruction error, so AQ minus its best rank K approximation, this is the sum of these very small singular values and is also extremely small. Now, setting q equal to 1 over epsilon is sufficient to kill off any singular value that is below sigma k plus 1 in comparison to any singular value that is above 1 plus epsilon times sigma k plus 1. So we know that if we choose our output to be the span of AQ times this Gaussian matrix, in order to obtain even this very coarse Frobenius norm error ensured by the sketching method, because this low rank approximation error is going to be extremely small, U tilde k is really going to have to align with large singular vectors of AQ. I already said we can't get convergence. We don't know that it aligns with actually the top k singular vectors of AQ, but we know that it aligns with some set of good singular vectors, and it gives us exactly what we need for spectral norm reconstruction error and for PCA error. The final step is we know that A and AQ have the same singular vectors, so if U tilde k is good for AQ, it's good for A, and this is the basic algorithm. There's some details in converting from this Frobenius norm error to the spectral norm and per vector error. And importantly, we always avoid talking about actual convergence of singular vectors or subspaces. So Krylov acceleration, the understanding of why this works is actually very simple. Basically, there are better polynomials for denoising A than A to the Q. Instead of raising your matrix to the 1 over epsilon power, you can apply a Chebyshev polynomial with degree 1 over square root of epsilon. And this degree saving is exactly where we're getting our square root of epsilon gain over the power method. Basically, the same argument goes through for applying this Chebyshev polynomial. The only difficult thing is how do we actually compute this Chebyshev polynomial? And basically what we do is we notice that we can just save the intermediate computations of the block power method into what's called the Krylov subspace, which contains all the components of this polynomial. I think I'm running out of time, so I'll just give a very brief summary of what we end up doing. Instead of computing the actual Chebyshev polynomial, we compute what is called the best span within the Krylov subspace, and this gives us the error bounds we need. We'll be around during the poster session for if you have more questions, and I can finish up explaining this. Thank you very much.
Well, thank you for a very nice talk. Before we start any questions, may I request all the speakers for the spotlight sessions to start lining up? Questions now? So let me ask you one question. Lanczos is, of course, intimately tied to this three-term recurrence, which is invokes the theory of orthogonal polynomials and makes things more efficient. So in your methods, are you using the three-term recurrence, or are you explicitly?
We're not. So yeah, really our method should be called the Krylov method, I guess, instead of a Lanczos method. You could use the three-term recurrence. The issues with the three-term recurrence is there's some instability. So in our actual implementations, because we're working with a relatively small Krylov subspace, we're just directly orthogonalizing it without using this recurrence. And this allows us to get a stable algorithm. You could use the three-term recurrence, but then you'd have to deal with all the stability issues that are inherent with this sort of approach. So it's not necessary to use the recurrence, basically.
So with these new methods, could you give a sense for, with the current computing power, how large of a matrix you can use practically, for a reasonable amount of time?
I probably can't give you a very good sense of that. I know that in doing experiments for this paper, if you have a sparse matrix with orders of tens of thousands or maybe a couple 100,000 rows, you can do this extremely quickly using the Lanczos or power method. So I can do this on my laptop essentially. But I'm not sure, I haven't done experiments on really large scaling of these things, but other people have done this, especially for randomized power method.
Okay, let's have one last question by Moritz.
Yeah, quick question. Great talk, Em. So the method you analyzed refers to the qth power of the matrix A, and so it's not really numerically equivalent to what you actually implement, where you have like a normalization step after every iteration. So it seems like to analyze that, you would need some kind of numerical stability at least, or cope with rounding errors in the iteration. It's the same for the Halko, Martinsson, Tropp analysis.
Yeah, right. So you don't really deal, even in the Halko, Martinsson, Tropp analysis, it's not really giving rigorous stability bounds if you're because you really do need to orthonormalize, if not after every step, you really need to orthonormalize relatively often after every few steps so you don't lose rank of that subspace. So we don't have a full stability analysis, but we have experiments, and I could show you later, basically showing that these Lanczos type methods are as stable at least as subspace iteration. in practice. And it would be interesting to think more specifically about what sort of stability analysis you would need to get a full analysis.
Okay, let's thank the speaker again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.